In this video, we start our investigation of systems of linear differential equations. We do not learn any solution techniques yet. This material is all preparatory. First, recall the definition of a system of linear differential equations. These P's are allowed to be functions of t, although when we actually learn to solve these, all the P's will be constant. A system is homogeneous if all of these F's are equal to 0. We will only learn to solve homogeneous systems. We can now rewrite such a system compactly as dx dt equals p of t x plus f of t. This P is a matrix that has these P's as its coefficient. This F is a vector of these F's. As long as these P's and F's are continuous on a common interval, solutions exist. And if we have n initial conditions, solutions are unique. So just as an example of this, suppose we have the following system of linear equations. We can rewrite this as a matrix differential equation. We'll now summarize some previous material that passes through into this setting. The superposition principle continues to apply. Theorem: let x1 and x2 be solutions to a homogeneous linear differential equation. Then C1 x1 plus C2 x2 is also a solution. The definition of linear dependence or independence also generalizes to this setting. So, definition. The vector-valued functions x sub 1 to x sub n are linearly dependent if there exists some list of scalars C1 to Cn, at least one of which isn't zero, such that C sub 1 x sub 1 plus C sub 2 x sub 2 up to C sub n x sub n is identically equal to 0. This is the 0 vector, the vector that contains only 0. Now that we have the superposition principle and linear dependence and independence, we get the concept of a general solution. So consider a matrix differential equation dx dt equals a x, where a is n by n. If x1 to xn are linearly independent solutions, then any solution can be written as a linear combination of those n solutions. So, for example, returning to this matrix equation, this and this are linearly independent solutions. And never mind for now how we got them, but because we have two of them. And this is a 2 by 2 matrix. We can form a general solution from them. This notation risks causing confusion, by the way. This x sub 1 and x sub 2 are vectors. They are not the variables x sub 1 and x sub 2 of the original system. So going back to this system, we have found this general solution. This vector equals an arbitrary constant times the first solution plus an arbitrary constant times the second solution. So going back to our actual variables, x1 is 3 c sub 1 e to the 2t plus c sub 2 e to the negative 5t, and x sub 2 is 2 c sub 1 e to the 2t plus 3 c sub 2 e to the negative 5t. Resist the temptation to combine terms. It's true, for example, that if c sub 2 is an arbitrary constant, so is 3 c sub 2. But if we replace 3 c sub 2 with an arbitrary constant b or something like that, we lose the fact that this must be 3 times this. In this video, we have seen that many of our previous terms and theorems generalize. Systems of differential equations can be homogeneous or non-homogeneous. Solutions can be dependent or independent. Independent solutions can be used to create general solutions, as long as you have enough of them.